So, hi everyone. So today I'm going to talk also about VPP. I'm going to take a concrete example. I'm going to talk about Levitation made handy, roll your own Maglev load balancer with VPP. So first, a few words about myself. I'm Nathan. I'm a software engineer working for Cisco. And I'm doing mostly container networking, VPNs with VPP, and also have a bit of trouble past with Python and JavaScript cloud applications. So before we start, a small bit of a word of warning. If someone is afraid of NAT66, please be aware that I might be mentioning that. Anyway, so let's get started. What I'm going to talk about is taking an example of cloud applications that you want to deploy in a typical cloud environment. And for it, you want to have good SLAs. So typically what you want to do is have a redundancy, which typically means having a load balancer in front of it. And you want that load balancer to have nice properties, like recovering for failures or seamless horizontal scaling. So one of the issues with out-of-the-box load balancing is that it comes with limitations, as typically your hash reshuffles when a set of backend changes. So that's why Maglev was actually made. And Maglev is just a smart way of doing load balancing that offers the nice properties that we are searching for. Namely, it's supposed to be relatively stable when the set of backend changes, which is exactly what we want. And also it has a few things that it's supposed to work with. It recommends working with direct service return, DSR, so that you don't have to store state in the load balancer. You just forward packet and don't care for the return. And that way you also spare a network hop along the way, which is good for performance. And one of the things in the paper is that it recommends working with a user space stack, but I'll come back to that later. So how does it work? In practice, what you'll do is you'll consider M buckets, and the buckets are going to be in a direction from flows to the application backends that you deploy. And typically you want to choose M relatively big, so typically 100 times the maximum number of backends that you'll want to have. And sorry, pop-up. So that you keep your hash space wide enough so that the backends don't collide too much. So what you are going to do is for each of your application backends, you're going to assign to them a preference list, which is going to be just a permutation of the set 1 to M. And then each of the backends will receive that list as a preference list of the buckets, and they will be with the algorithm on the side choosing the buckets by their preference. So the reason we do that is this will ensure that the backends to bucket mappings will stay relatively stable when the set of backend changes, because each of them is more or less guaranteed to get its first pick and then its second pick and so on. And then when you have incoming flows, what you'll do is just regular hashing. You pick a bucket, and that bucket gives you the backend pair of the previous mapping. And that's it. That's all you have to do. Your flows are load balanced, and life is good. So to give you a bit more colors on why this exactly helps, if we take an example of two backends, so here one green and one blue, and we have with their respective preference list, and we have them choose the buckets. We load balance a few flows that go into the bucket list. And when we consider the addition of a third one, a red one, what will happen is that obviously that third backend will take a third of the buckets, so probably a third of the flows. But it will leave the rest of the mapping mostly untouched because of the preference list. So both blue and green, they will keep their preference list, and so they will most likely keep their set of backends stable. And given that the number of buckets is high, you have a huge likeliness of having the same mapping in the end. So that way, the flows reshuffling stay relatively minimal, which is not the case if you consider a naive load balancer based on just a hash and a modulo of it. So that's for the theory, but how do we make this work in practice? So if we go back to our application and we say that we deploy it in a cloud provider in VMs, and each VM has its own IP address, One thing that we have to account for is that ingress is typically constrained. So you have to go through an infra construct that typically already does translations on some kind. And at the same time, egress is also constrained because you typically don't want to send any packets as a cloud provider. So what will make it hard to do DSR? Because you basically, as an application, you cannot issue packets to an IP from an IP that is not assigned to you from the infra's perspective. Also something to note is that if we want to do direct service return, we will need additional configuration into the applications themselves, because typically you want encap and you want to terminate packets to an IP that is not yours. So that brings in additional complexity. So for the sake of simplicity in this example, I'm considering NAT instead of DSR. That is that all Maglev instance will receive packets to its IP, NAT them with the backend IP it chooses. So ironically, one of the issues is that we have now to keep state around, but nothing forbids reverting back to the uncaps if we manage to extract the constraint of the deployment. So let's consider our load balancer. What we'll do is provision a VM, and we want the packets from the client IP to our VM's IP to be source natted, to be destination natted to the backend IP that we choose. So that's the Maglev part. And be source natted with the VM's IP so that the traffic flows back to us and we can undo our work. So in order to do that, we need an implementation. Unfortunately, that's not something that's natively offered by the kernel. But also, as in the algorithm, there are many important implementation details and also parameters that you need to input. It's probably not going to be able to be leveraged out of the box. And also, a third point is that we want this to be quite performant, because we will want to handle the traffic of all the backends on a single VM. So that sounds like a great use case for user space networking technology like VPP, and that should not really come as a surprise, being in the name of the talk. So yeah, let's start VPP then. So in order to do that, one thing you can do is just issue that command line. So you pick a relatively recent release of VPP, you throw in a few stanza, basically you pass it the PCI ID of the interface, and that's it. The thing is running without anything more to do. But if we do that, one thing that might happen is that if we have a singular interface, which is the case on most VMs that you spawn up for starters, you will lose access because VPP has it, but not the host anymore. So ideally, if we want to solve that, we'll add an extra management interface, but not every deployment has this lying around. So we're a bit screwed if we go that way. And something that would be nice is to have a way to somehow duplicate ETH0 inside the host. So fortunately, that's something that we can do, making VPP act as a bump in the wire using what we call the pun feature, meaning recreate a tap interface in Linux, give it the exact same configuration as in the host, and just tell VPP, pass every packet that you don't know what to do with to the host. It's quite ugly from a networking perspective because you're sharing IPs and that you're not supposed to do that. But one of the benefits is that you're making the host life transparent, and you manage to keep your SSH sessions open. So that's at least something. So now, if we go back to our Maglev story, now that we have a VPP instance running, what we need to do is just add the Maglev magic to it. And just leverage one of the nodes available that was presented before. That's going to do the fetching of the packet data, looking the appropriate set of backends, and just rewriting the addresses as we need. So for that, we'll leverage a plugin called CNAT, standing for the demonic child of cloud and network address translation, for lack of a better name, that already has this kind of logic implemented, because we don't want to redo all the checksum computations ourselves. And the thing that we still have to do is make that piece of code aware of the IPs that we want to rewrite the packets with. So for that, writing control plane logic in C is quite cumbersome. So what we'll do is spawn an agent. So I choose Golang because I do that on my spare time. And that way, what this allows us is to leverage our favorite library of the moment. So you can throw in console, etcd, just pull whatever from GitHub. Access whatever service discovery mechanism you have available. And then open a connection to VPP and talk to it through the binary API without. So basically, you split a bit the control plane and data plane logic. You have all the complex and event-driven logic in Golang, and then you cross the binary API, and you're just in C doing data plane. And that can be done relatively easily. You have an API library available. You just instantiate a connection to VPP. You tell it that you want to maglev NAT the TCP port 80 to your own IP, and that you want to balance that to the set of backends that you have available, and that's it. You can now talk through VPP to the backends using the Maglev's VM address. So that's it. Things are working, but I think it's still worth asking, why did we do that? Do we regain something? So I argue doing that brings in a few benefits. So one of them is that we now have full control on the load balancer, how it's implemented, how it's configured, all that. It's portable, which speaks for deployment uniformity, meaning you have the same behavior regardless of where you deploy that. If you have multiple cloud providers, if you're testing locally, you have the exact same behavior. And also, the thing is relatively lightweight to deploy, meaning you have a container, you can run it fairly much everywhere. And underneath, you have DPDK or some driver that allows you to swap the interface that you consume. And finally, regarding performance, we should be mostly, on a given VM, we should be mostly I/O bound on most of the instance types, so throughput shouldn't be an issue. PPS, likewise, it should be way over the capacity of the instance. And that last one actually raises a question. If we are I/O bound on the VM, that means that we don't use all the other VMs. So we have spare CPUs that we don't know what to do for. And also, before we were talking about NCAPs, which means that we actually see that ideally we will need to do more network processing on the backends themselves. So that actually means that one thing that we could do is collapse the whole infrastructure and do everything in the same place, meaning having the backends running directly on the VM of where we do the maglev. And so if you collapse the whole thing, what actually you end up doing is doing some kind of container networking. Actually, this actually leads us towards a solution that's more something like what Kubernetes does. And so that's actually why this first project and led us to envision something like Calico VP, which is doing container-to-container networking in VPP itself, leveraging the control plane that Kubernetes provides, and actually having the best of both worlds with Maglev support. And that's it. Thanks a lot for listening. Hope you enjoyed the talk, and just time for a few questions if you have.